Good afternoon, everybody. The title is self-explaining. I'm going to talk about the improvement we did at the material level to enhance the fatigue life of shared memory wire, especially focused on industrial application, I guess, used in automotive, domotic, white goods, and so on. In principle, as actuators. But the story starts, I would say, 5 years back, at least, when a question came up in our R&D department. So, is it worldwide to develop low inclusion nickel titanium alloys to improve fatigue behaviors? Until then, I would say the effects of the material structure on the fatigue received not so much attention, especially related to the topic of inclusions. But most works was dedicated to monotonic study of monotonic properties. Relatively few works were done at the time on the effect, in understanding the effect of inclusions, but without any systematic approach and without clear, I would say, comprehensive study and conclusions. Also, the regulations today used for, especially NiTi or for medical devices, allows inclusions up to 39 microns, but this measure is carried out typically at the semi-finished products. That means that at the end, on stent, on fine wires, and so on, the inclusion size, the maximum inclusion size, is unknown. But quite recently, several works, systematic studies were done by different groups, and they at the end came to the conclusions that the inclusion size has effects on the fatigue behavior, and it is one of the most important effects of inclusions. Some statements before presenting our work are necessary. In our experimentations, and this is the first part of the story, we try to understand if there is some effects and what kind of effect has the inclusions. Well, typically, as you know, most of you knows, looking at the fracture surface of, for example, of a nitrile wires is not unusual, but typically always is present at the track tip and inclusions. In this case, is what we call typically intermetallic oxide, Ti4 Ni2 oxygen, sometimes not stoichiometric, and sometimes titanium carbide, that is the other main inclusions. The differences in carbon and oxygen content. Most of the people look at the gas impurity level to say something about inclusions. But the carbon and oxygen content between different melting approach, typically used by melters, and so you can, I talk about commercially available materials, does not result in a measurable difference in fatigue resistance. And that's one other important point we will get back in a few minutes. So looking at the carbon and oxygen is not conclusive about the inclusion size, the air fractions, the effects on fatigue. Our hybrid VIM-bar approach on nickel titanium productions brought to the conclusion that standard superelastic alloys used in biomedical applications as the main inclusions are represented by titanium carbides. This means that it doesn't mean that intermetallic oxide are completely absent. While on the other hand, in shared memory materials plus 95 transformation tablet, the main inclusions are intermetallic oxides. Our works in understanding the effects of inclusion of fatigue was focused on superelastic wires, and these are the main conclusions. We analyzed a lot of failed wires after different fatigue testing by using rotary beam test, and we analyzed the fracture surface, and we at the end found that the inclusions at the crack tip follow typical Gamble distributions. The population and different materials follow a different. You can see different Gamble distributions function. And in this way, we were able to distinguish the effects of different inclusion types and size and distribution in different commercially available materials. On the other side, looking at the extreme inclusions that we use in this approach by also following the recommendation of ASTM E2283, sorry, that are the recommendation for, in general, ball bearing steel, high performance steel, but we apply this procedure also to NiTi. The most important conclusion is that one, where the fatigue limit measured from our, I would say, strain life curves are perfectly correlated to the max inclusions size at a fixed return period. You can select 100, 1,000, whatever you want, but the relations is always the same. There is a perfect relation between the fatigue properties in terms of fatigue limit, but not only, and the extreme inclusions. Well, as always happens in industry, there is a second part of the story to continue the R&D activities. We need a motivation to improve, to make efforts in improving materials. And the motivation is represented here, especially in industrial applications as shape memory actuators. The SMA's wires are growing their use because the bigger players in these fields, in the industrial devices, are exploiting shape memory advantages, especially due to the very high force-to-weight ratio of wires, especially of very thin wires, to conceive and to produce new devices, new actuators. And these are two most important examples. One is a pneumatic valve for the control of comfort seats in cars. On the other hand, another important and with very high expectation from a mobile phone manufacturer is the camera modules based on shape memory technologies for optical image stabilization and autofocus of video cameras of the smartphones of next generations. In this case, 76 micron wires are used. In this case, 25 micron wires. We are talking about very, very thin wires. And what is the problem? The problem of inclusions become bigger and bigger, reducing the size of the wire, the cross-section of the wire we would like to use, as represented here. So we had a motivation, an industrial motivation to improve the fatigue of our materials, to allow faster growing of the industrial application, for example, what I reported in the previous slides. And this was reached by a very hard review of melting and processing of the materials. I cannot enter too many details, but we did a huge amount of preparation in terms of ingot, semi-finished products. We improve and control our processing conversion parameters. We improve also the control and selection of raw materials, and at the end we were able to reach the goal. And I'm going to show you the results. The results is a comparison between our standard 25, 76, 100 shade memory wires. Smart flex wire is our standard trained actuators. Titanium rich standard AS 90 degrees C, and we prepare ingots with a new combination of melting and processing by keeping constant everything at the end in terms of cold board, surface finish, final annealing and training, in order to neutralize as much as possible the secondary effects on fatigue behavior. We check also the gas impurities and transformation temperature. This is our standard historical reference, standard beam bar materials and our improved alloys. As I mentioned at the beginning, looking at the carbon and oxygen doesn't happen in having some indication about the potential inclusion size or area fraction and the effect on fatigue. And that's an important outcome from our R&D activities. Then we analyze and perform in-house inclusion analysis following the recommendation of ASTM F2063, that is the standard practice for nitinol used in biomedical devices. Historically we developed an internal procedure, and just to show you a couple of pictures on this is the this is the representation of a longitudinal cross section of a 6.35 millimeter coil. Is a semi-finished product in the range of the standard practice, and the same size of the improved alloys. This is only a qualitative picture, but these are the numbers. The numbers show that on shade memory formulation, titanium rich, the max inclusion size is reduced of more than 5 times, and the average inclusion size, which is important, is of the improved alloys is systematically below 1 micron, with more than 90% of inclusions below 3 microns. We characterize the wire to be sure that everything was perfectly in line, and I don't enter in details about the characterization method. We typically are the uniaxial constant force thermal cycling and the fatigue testing according to the sketch reported here. I would say the hysteresis curves are similar, so no anything special or any significant differences. And these are the fatigue testing. We select here 350 megapascal, which is quite stressed conditions for 25 micron wire in this case. You see in red the wires produced by the improved alloys, and in black the standard. In black 3.5% strain is the maximum we are able to reach. Did not survive more than 1,000 cycles, increasing the strain amplitude of load. We fix our run-out criteria at 150 K cycles, and these are the numbers. Just to give you again the numbers for these conditions: 3.5% strain, 350 megapascal stress, and you see that on 25, 76, and 100, even if in the case of 76 and 100 micron, we still have to work to increase the statistics. The differences are quite evident, both on the average and on the minimum number. We are in the range 2 times, 8 times the standard materials. But by changing the conditions, so in less aggressive conditions, we observe an improvement of the fatigue life over 100 times of these low inclusions wires. So we also check, and this is quite evident, we check also the fracture surface of all the wires, all faded wires, just to apply again also on this material our extreme value statistics. And this is clear also in this case. The distribution of extreme inclusions is completely different. We move to a very, very low inclusion size in the improved wires. So we are almost always below 3 microns at the crack tip in terms of max inclusions observed. Just to conclude, okay, this is a summary just to explain how effectively we improve the materials, and the wires are ready for high volume production of the devices I showed you before, and for micro actuators of next generation. And thank you very much for your attention. I'll be happy to try.